So, and the idea of what do we do with huge and tiny numbers that we mentioned last time, one option is scientific notation. So like the national debt is changing constantly, but the last one I grabbed was $26.7 trillion, and there's around 331 million people in the U.S. Those are both some big numbers. They're written in what we would call word form. Now, word form could also be like writing out really, really long things in words, like 26,489,000,000 and all of that, but this is more likely what we'll see in terms of word form. They also could be written in standard form, which we are going to try in order to calculate what the national debt per person is. Great news, when it says per in there, I'm thinking of division, and so I know that what I actually want is debt divided by the number of people in the U.S. So the national debt is 26.7 trillion. So let's change that to scientific notation. Not scientific notation, sorry. To just standard form. So that's a lot of zeros. A lot of zeros. And then the bottom would be that there's 331 million. So that's still plenty of zeros. Not quite as bad, but pretty good. And then I can divide those two. And I get, let's round to cents because it is dollars up here, dollars per person. So that's around $80,665 per American. I don't know if it's actually American or people in the U.S., but that was less to write. So we're going to go with that. So that's the national debt per person. You may have seen numbers around that size reported before. It's not the only, national debt problem they give us, but you can see right now that writing this $26.7 trillion that way was kind of painful. So what we also have is scientific notation, and your calculator will take numbers in scientific notation, which means you don't have to count how many zeros you type, which for me is very encouraging. So what would this 26.7 trillion look like in scientific notation? So what we have to remember about scientific notation is, first, the number has to be expressed as a number between 1 and 10. Now, it actually can be 1, but it can't be 10. So it can include 1, and then it's multiplied, so it's some number, often with some decimals after it, that is then multiplied by 10 to some power. And we use positive powers to express that this is a larger than 1 number, and we use negative powers to express that this is smaller than 1 number. So how would we do that here? Well, we would start with 26.7 is not between 1 and 10. So we would need to change that to 2.67, okay, times 10 to the, and this would be a positive number because this is a huge number. And what I would do in my head is recognize that trillion is 12 zeros. And then we need to go an additional 1 because the decimal point gets moved all the way up here. So that would be 13 decimal places that it has moved. Then 331 million would change to 3.31. Again, not because we need 2 decimal points after that, but because before the decimal point, I have to have a number between 1, including 1 possibly, and 10. So that would be 3. And then this would be times 10 to the, and again, thinking about millions, that's 6 zeros. And then I'm going to add an additional 1, 2 spots to get to 3.3. And it bothers some people that I'm going to the left and adding to get a positive 8. But remember what the positive stands for. It stands for a large number. And the bad news is you can't do like right's positive, left's negative to go both to scientific notation and back to standard notation because it only works one of the ways. So that's why big numbers bigger than 1 have positive exponents. Numbers smaller than 1 have negative exponents. This would actually type into your calculator pretty simply, and you would get the same answer. And you wouldn't have to count how many zeros you were typing into your calculator is the perk to that. Let's practice some of these. If you feel real comfortable doing this, you can try it and then come back and check your answers. Scientific notation in your calculator is often written instead of this times 10 with the letter E. So this would say 8, and then I replace the times 10 with E, and instead of writing the -5 in the exponent, it's just written as a capital. Because on a really small calculator, it's hard to tell what's superscripted and not superscripted. You're pretty spoilt with your calculators, but we had some pretty not that technical ones back in the day. So now, what would this be in standard notation? So here's what I recognize. Currently, the exponent is negative. So this means that this number is actually less than 1. So when I go to write this, I'm going to write my 8, thinking about the decimal right here. And then I want to get it small. So I'm going to move to the left 1 and be in front of 8. Another 0. Now I've moved 2, another 0, I've moved 3, another 0, I've moved 4, another 0, I've moved 5, and add in my decimal point. I'm going to throw in one more 0 just to hold its place. And I'm going to test this. If I moved my decimal point 5 places, would it be here? Yes. And is this number less than 1? Yes, it is. All right, let's go in the other order. Let's start with standard notation. Again, I noticed in standard notation that this number is less than, sorry, I shouldn't run X yet. I haven't showed y'all that and you don't want to see it. Less than 1. So I start with, how does scientific go? Scientific notation go, I've got to have a number between 1 and 10. So that means I'm talking about 1.04. So here's my number less than 10, 1. Here's the rest of it. Notice I don't drop the 0 between the 1 and the 4 because I do want to represent what I originally had, not just record non-zero digits. Times 10 to the, it's going to be negative to express the fact that this was less than 1. Let's see how far that decimal place is actually moved. 1, 2, 3, 4, 5, 6, 7. So pretty small number. And then, of course, scientific notation in your calculator. I just want you to have seen this a few times. The times 10 and the raised part's all gone, and then it just has -7. On my math lab, when you go to type this in, they are going to expect you to use their times 10 raised to button. So the good news is it saves you time, but you'll have to look for it over in your toolbar. If it says you're wrong and your answer looks just like their answer, try it with that times 10 raised to button instead of just typing it all in yourself. Alrighty. Moving on. Now we're given it in scientific notation in our calculator. Let's put this in regular scientific notation so the numbers stay the same, 9.143. E is actually the representation of times 10 raised to, and then our 8 gets superscripted up here as an exponent. So what I notice is this number is actually going to be larger than 1 because I have a positive exponent. So I'm going to start with the 9, and then immediately I'm going to start writing numbers and moving the decimal point. So I'm going to move it to past the 1, 4, and 3. So that's 3 decimal places. That leaves me with 4, 5, 6, 7, 8 decimal places to go. I don't write the decimal point because I don't have anything to go after it. And then we, of course, add commas to help us kind of identify what size of number this is. So this is around 914 million. We got e to the 8 to see that. So millions is just 6 decimal places, but we're in the 100 millions is why we have 8. So let's work with a few more ratios here that you may have seen. Just one, I want you to start thinking about this per as just division to help you tackle what we've got coming in the rest of this course. And 2, I want you to see how just a slight word change can change so much. So next thing we're going to do is, what is the national debt per working American? So we already know that there's $26.7 trillion in the national debt, which we've written as 2.67 times 10 to the 13, I think. I'm going to scroll up and check. Yes. Now, so this is the national debt. Per means we're going to divide. Okay, that looks like a percent sign. Sorry, so I'm just going to write it here. Divide working Americans. So while there's 331 million people in the U.S., only 153 of them are working. So that's 1.53 times 10 to the, what was it for millions? 8? Yep, for 100 millions anyways. You don't have to convert these to scientific notation. I'm doing this to make a point. You can write the numbers as they are with all the zeros in it and then tap it in your calculator. That's why we have them. But I do want you to notice then that this is going to be a number larger than 1 because we have this top, which is 10 to the 13th, and this bottom that's 10 to the 8th. So there's actually 5 additional zeros in the numerator. Just something to note. So when we go to divide these, 2.67 divided by 1.5, in my head I'm thinking about how this is a little less than 2. And so what I actually end up with is 174,509.80. If we wanted to round that to dollars, we'd have 174,510, whether they want dollars or cents. And this is debt per working American. So see how I said it was close to 2? We've got this, and how this is 5. 1, 2, 3, 4, 5 tens larger. So it all kind of goes back to that. Now this is larger than our debt per Americans, right? Or per people in the U.S., however we're interpreting that data, because we divided by a smaller number. Remember your rules of division. So this might be reported if you were trying to grab attention, or some people think this is a better description because people who aren't working aren't really going to do anything for the national debt other than possibly hurt it a little bit worse. So interesting. Not something I want to debate here though. Moving on, how much credit card debt is there per credit card in the U.S.? So people in the U.S. owe around $988 billion, and this is on 1.2 billion credit cards. Now, we're going to love this problem because if this is debt, 988 billion credit card debt, per credit cards, 1.2 billion, I don't have to do any adding all the zeros in. I don't have to do any changing this to scientific notation. I just can divide 988 by 1.2 because it's all in billions. And this is going to give me something I would think pretty close to 900. When I typed it in my calculator, I got $823.33. Now this is per credit card, and this actually paints a much better picture than what you might have seen on other situations. But I'm going to quickly prove that that's a terrible number. This makes things look better than they are. Yep, I'm taking time to write it because this is a big deal. I didn't have anyone teach me about credit cards, and I learned the hard way. So that's not going to get to happen to you unless you've already learned it the hard way. This makes things look a lot better than they are. Why? Because there's actually only 190 million Americans with credit cards. So if I wanted to calculate the amount of credit card debt per people who have credit cards, what would change? Well, this would still be 980 billion, but this would now be 190 million. And I'm going to make a point that if you don't like my next step, you could always add in all the zeros for billion and then all the zeros for million in the denominator and divide. I'm going to do a little bit of funny math and say that this then is actually 988,000 million, like recognizing that there's 3 zeros difference, and this is 190 million, and I'm doing that to get rid of those. You could do a similar thing in the world of scientific notation and saying, you know, that this is 10 to the 6th and that's 10 to the 9th, so that's where I introduce these extra 3 zeros is 10 to the 3rd. Anyways, I'm sorry I got really mathy there. Let's go on and divide. So this would be 5,200 per credit card owner. Okay. And again, this isn't terrible, but that is money that they don't have and need to be paying off. But notice again, this is just per people who own credit cards. You probably know people who have no credit card debt and have credit cards. Like we probably have one stashed around here somewhere. Maybe. I don't know. I assume we're on this list. But there are some people then, if this is the average, that own quite a bit more than that. And this is just credit card debt, not including other debt. So this is bad. And if we divided this, like again, we could divide this per American. It's around, it's a little less than 3,000 per American, or per working American, and it's a little over 6,000 then. Which is the same number. Like, don't even have to go research or get a New Year's date. So, lots of things we can do with that number. Isn't that crazy? And so, when you read this data in everyday life, watch the per. Like, watch this, what this has been divided by to get this particular number. Sometimes, again, they pick something because they're trying to get you emotionally attached to a value or to think it's not as